continuing with stereochemistry. Let's go ahead and do a problem. This is actually pretty close to the one that's on the lab, but I changed it just a little bit. The one in the lab had 2 double bonds in it, and then the chlorine in the middle. That compound is actually achiral because there is no point of difference on the left and right groups. This one is. So one issue you may come across, which is a common thing with these problems, is what is priority 2, what is priority 3? All right, so priority 1 here. Okay. Sometimes when you're looking at these pieces here, it might not be very obvious, but we need to look for the first point of difference, look for a tiebreaker. I recommend that if you're having a hard time seeing it, just go ahead and draw it out. So I'm just going to draw out this, but I'm going to draw it in a little bit more detail, showing all the atoms. So the H was implied. And then going 1 atom out, they are carbon, they are still the same. We need to go 1 atom out again, and again, and again, until we find a point of difference. All right, so notice here how this carbon has a double bond, this one doesn't. It's going to work out where the double bond gets priority, but the way that's figured out is you think about what that carbon is attached to. So this carbon has attached to hydrogen, and it also has 2 bonds to carbon. So that's what you want to imagine when you're looking at priorities there. So here we have an HCC versus 2 H's and a C. And that's your other methyl group over here. So we have a tiebreaker here. We have HCC versus HHC. This is the larger group. So it works out where the double bond, the triple bonds, basically the more bonds of carbon you have, the higher priority it's going to end up being. So what do you think the designation here is on this? Yep, it's S. So it goes 1, 2, 3. It's going counterclockwise. It is R. Okay. So basically, oh my gosh, we just said S2. 1, 2, 3, counterclockwise. It is S. Yep.
Since the H, which is the lowest one, since it's facing us, don't we have to look at it from a different angle?
It's not facing us, it's away from us. Yeah, the dashes are away, so we give it the designation as we read it. Okay, go ahead.
No problem where the H is with, or where it's with.
I'm going to do the next one where H is in the plane of the paper.
Okay.
Yep. You actually have quite a few, you have like 4 of those on the lab. So I wasn't trolling. You guys have to know how to do those too. I had a student a few years ago tell me that being an organic chem professor is being a professional troller. I was like, no, it's not. You're agreeing with them. I should have said anything. All right. All right, let's go ahead and put a ethyl here. Okay, so in this case, when they're in the plane of the paper, it may seem ambiguous. But what you need to do here is you need to actually strictly follow the rules for stereochemistry. Technically, you're supposed to be looking down the carbon low priority bond and then assigning your priorities. So we're going to be looking at this from this perspective, straight down. So we can imagine, we have our little eyeball that I'm going to draw in here. So that's the view. Little eyelashes on it, so you can tell it's an eye. All right, not a tent. All right, so it's looking at it this way. So if we draw the Newman of it, it then becomes very apparent what the stereochemistry is. Okay, so the way I'm looking at it from this perspective, I went ahead and just determined that chlorine was down. So that means that this part would appear to be up, and this part's down. So the question is, the tricky part is, okay, does the ethyl go left or the ethyl go right?
Left.
It's left, yes. If you're having trouble seeing this, you have to use the model kit until you get comfortable with it. So ethyl is left, methyl is right. So what I kind of visualize is imagine that you're like putting your head to the paper and that these things are actually like popping in and out of the paper, like which way would it be going from your perspective. So if I looked at it from this way, that looks like it would be pointing, like if I put my head, like line it up with this right here, that would appear to be my right, the way it came out. So I just put that here in the Fischer. Okay, and then the circle there, what is that circle representing? Is it a carbon?
No, it's not.
It's the H. Yep, so you don't have to have the groups coming off the back atom if there's nothing coming off. That back atom is H. That's just how it looks. All right, now we can go ahead and assign priorities. I think now it's very obvious now. It's 1, 2, 3. So then it goes like that. That is a R designation. Yep. Let's use blue. Mix it up a little. R designation. Okay. Another problem that you may come across that has to deal with Newman projections is if you're given a Newman projection, it might ask you if it's R or S. I think these are pretty tricky. So I want to go ahead and do a practice like that. All right, so H3C, BR, let's make that an H. And then let's go ahead and make this a CH2, CH3, and H. Okay. All right, so what I want to do is take this Newman projection and I want to convert it to a dash wedge drawing, and then I want to also assign an R and S to it. The thing with these kind of problems is I recommend getting into the dash wedge first before even trying to do R and S on it. Because it looks like it's kind of a weird perspective. The H is kind of like coming towards us. And how do we rotate here? Let's convert it to the dash wedge. So basically what I imagine here is that you just pick a side. And you want to imagine what you're going to see if you look at it from the perspective of the bond line drawing, which is typically from like this point of view, from that angle. It's typically the angle that we draw them from. There's your little eyeball. All right, so first things first, how many carbons are there? So there are 1, 2, 3, 4, 5. And then based off the angle on this, how it's coming downward, I'm going to start with that coming downward, like that. And then the front carbon here, this dot here in the middle, that is carbon 2. And then the back carbon is carbon 3, the way this is drawn. If we're looking at it from that perspective, should the bromine be a wedge or a dash? So look at what's happening with the H and the BR.
Oh, it should be a dash.
It should be a dash. Yep. So see how the H is coming towards the view, and this is going away from the view? So that means that the bromine is a dash. So notice here what I did here. I basically I'm looking at it from the perspective where the main carbon chain would be flat. Or like a wall right in front, and the only thing really three-dimensional about it are the wedges and dashes for the branch groups. So in this case, H is coming towards the viewer, BR is going away from the viewer. So now we can do a designation on this. What is it? The R or S. That is S. S. So it goes 1, 2, 3. Okay. Let's do one more of these. So this time, I'm going to mix it up a little bit. So let's make this go like that. Oop. Actually, let me just start a new sheet of paper here. I got the wire in the way. All right, let's go ahead and do a new problem here. All right, so 2 methyl groups, an H. And then let's go ahead and have a Cl, H, and then let's say this is a propyl. PRO is for propyl. So how many carbons total do we have on this? At least in the parent. How many carbons are in the parent? 1, 2, 3, 4, 5, 6. There's the 7th one is this methyl, so there's 7 total. Is that front carbon a chiral center? No. That has 2 of the same group. So that is basically your isopropyl group. 2 methyls, it is not. So we have a 6 carbon chain. And I'm trying to think which way I want to draw this. So 1, 2, 3, 4, 5, 6. Okay. So this is the front carbon. This is the back carbon. And let's go ahead and just make sure we're clear on what's what. Front, back. We could draw it in 3 dimensions if you wanted to. We basically, if we're looking at it from, let me say, oops, fucking Morton. Go away. I'm not idle. Let's go ahead and just choose this perspective. So I want to look at it from this perspective. I want to try to get as much of the chain as possible in the plane of the paper. So if we look at the front carbon here, which way do you think that wedge, if we're looking at it from this angle, which way should that wedge be going? Towards or away? Or with a wedge or a dash, I mean.
Is it away?
It's away. Yep. So the H is coming towards the viewer, methyl is going away from the viewer. So that's going to make that a dash. All right, because of the way that this is kind of twisted, I'm going to try to represent this as much as I can. So what about the propyl group? So I'm going to fill that in here and have the same rotation as this is. That should be a wedge coming towards the viewer. In this case, we can say the chlorine is in the plane from the perspective that we're looking at it from. So basically what I did was I put the chlorine to the methyl here in the plane of the paper. I think now we can go ahead and give a designation to the chiral center. All right, so this is the chiral center here, and I'm going to go ahead and draw the H in. This is the H going away from us. Priority 1 is what? Chlorine. And then the tricky part is priority 2 or 3. What do you guys think? Is it going towards the left or going downward? That's priority 2. It's actually going towards the left. So here we have to go by first point of difference. So this is a CH2, CH2, CH3. That first carbon has 2 bonds to H, 1 bond to C. This first carbon coming off has 2 bonds to C. This is higher priority. If you're ever having confusion of it, you can just make a little list of what that carbon is attached to, like 1 carbon at a time, until you get a difference. So it works out where priority 2 is towards the left. So with that in mind, what is the designation? It's S. Yep. S. I'm not going to put a bunch of these on there because I know I am aware that they are challenging. Just make sure that you try them at least. I will put it out on the exam. There will be at least one where you have to go from the Newman projection and be able to get the designation on it. Huh? All right. I did want to show you guys another type of projection here. So we did have Newman projections. Those are for bond rotations. Yep, Fischer projection is the other one. I do want to point out that Fischer projections are typically used for carbohydrates. We will revisit Fischer projections next semester. But for now, I want you to be able to recognize them and how we read them. Okay, so basically what a Fischer projection is, it's a different perspective on looking at the drawing here. So I'm going to go ahead and draw a normal tetrahedral. And I'm going to go ahead and label some groups. So let's say this is A, B, C, D. And essentially, the perspective on the Fischer projection is looking at it from an angle where nothing is in the plane of the paper. So it is possible to do that with the tetrahedral. If you look at it from exactly this angle, what we should see is 2 wedges coming towards the viewer, and then 2 dashes going away from the viewer for group C and D. All right, so let me go ahead and represent this here. So I've heard people call these the bow ties. So basically, there are 2 wedges coming at you, and up and away is, let's say it's the C, and then coming downward is D. Okay, so by doing that, should A be left or right? Should be left. It's left. Yeah, we're looking at it from this perspective. A would be towards your left. All right, so A and then B. And basically what a Fischer projection is you take this perspective and you smash it, squash it. And then that's your Fischer projection. So the tricky part about these is that the horizontals are towards, the verticals are away. So on a Fischer projection, vertical is away, and then horizontal is towards. And the interesting part about this is it's almost like they were trying to make it confusing the way this is drawn, because typically these are done for carbohydrates, and it works out most of the time for carbohydrates that priority 1 and 4 are on the horizontal. So you're going to have to assign the priority like normal, but then give it the opposite designation. So let's go ahead and look at a carbohydrate. So typically the way carbohydrates are drawn in a Fischer projection is they will put the most oxidized carbon up. So that's basically what the carbonyl is up. And we'll definitely revisit this next semester, but for now I just want to do an example. So carbonyl is typically upward, and then your bottom carbon is typically a CH2OH, and then you got a bunch of OHs in the middle, and those are your chiral centers, are the OHs in the middle. Let's go ahead and take a look. So here we have, let's say, OH, H, OH, H, HO, H. We're not going to have enough time today, but I do want you guys to practice for the exam. I'll go over this on Tuesday maybe. But we should. Because I want to do some harder problems, but you should be able to know how to go from dash wedge to Fischer as well as part of this content, and identifying whether or not things are the same or not. All right. So here I want to go ahead and give RNS designations to them. But before we do that, though, I do want to talk about D and L sugars. So typically the way D and L sugars work is we take a look at the bottommost chiral center and the direction of the OH. So it turns out that if the last OH in the Fischer projection is to the left, that is the L enantiomer, and then if it's towards the right, it is the D enantiomer. So we're looking at Fischer's again. Oops, there's no C in there. Ah. Stayed put. So, I'm spelling it the British way there for a second. All right, so then we look at the last OH. Let me bring this down a little. We look at the last OH, and then if it's towards the left, it's L, and then towards the right, it's D. Oh, let me add the word chiral in here, the last chiral center. So D equals, what was that again? Right. And then L is towards the left. They're actually short for dextrorotary and levorotary, for which direction they're pointing, like so. So if you ever see sugars with like D glucose, they're basically saying that The last OH is towards the right, and that the rest of the OHs are in the orientation to be glucose. It turns out that every single possibility of which directions OHs are going in, they're all given a different sugar name. But if you flip everything over, we keep the name the same. So if you flipped everything, we would then have like L or D. We'll go over this a little bit more on Tuesday, but for now, I want to go ahead and practice doing RNS. But we'll go over a little bit more carbohydrates on Tuesday, and then we're going to go into even more detail in 242. The cool part about carbohydrates and the fact that they're Fischer projections, I would argue that most of the time, priority 2 is up. And that's the cool part about things. If we're always drawing them in the same orientation, it works out going towards the carbonyl and it being a tiebreaker. So, all right, so take a look at the first one here. What is priority 1? Yep, the OH is priority, so don't think the carbonyl is priority. It is the OH by the first point of difference. So let's use purple for fun. All right, so priority 1. Okay, so then we go the next atom out. Okay, we have carbon, carbon, and then you look at what that carbon is bonded to. This carbon has 2 bonds to O, 1 bond to H. This carbon has 1 bond to O, 1 bond to carbon, 1 bond to H. The 2 bonds to O is the tiebreaker. So it's going to work out for all of these that going upward is priority 2. So a little trick that I'm giving you guys. Okay, so so how is that going? Is it going clockwise or counterclockwise? Counterclockwise, but we're looking at the back because everything in the horizontals are towards you. So you give it the opposite designation. So counterclockwise, but we're looking at the back, so it's R. Yep, this is R. And that's the tricky part of Fischer's, is that right here I have the little comment that horizontal is towards you. So if the H's are towards you, then we give opposite designation. All right, so next one here, what do you guys think of that RS? So for carbohydrates, the OH is always going to be priority 1. Priority 2 is up. Yep, so it goes 1. It's the same kind of thing as the first one. So that is also R. And then the next one? S. Yep. And is that dextro or levo rotary? Levo, yeah. The bottom OH is left. The things we're going to be doing next semester to make this a little bit different is we're actually going to cover the chemistry of how alcohols and carbonyls react next semester. And we're going to see that this OH can kind of go here and make a ring. And then we can draw the Haworth projections. We'll do it next semester. But the Haworth projections are what they typically show in your biology textbook. They show like the ring structures for all the different sugars. Those are the Haworth projections. So typically the way this is done is people will get the dash wedge drawing, go to the Fischer drawing, and then to the Haworth drawing. And by the time you get to that stuff next semester, I will actually use this as a way to revisit stereochemistry, because you'll probably haven't seen it in a half year by then. All right. So I want to go ahead and take a look at some of another harder problem type. Make sure I think I covered everything. Actually, I want to go ahead and take a look at an amino acid, just for the sake of discussion. I think I want to do the one that has a methyl group. Let's take a look at cysteine. I did mention that the main thing that we use Fischer projections for is carbohydrates. It's also done often for amino acids as well. They use the same convention for amino acids, where the most oxidized carbon is up, and then the bulk chain is going downward. So it works out where the amine group here is going to be on the horizontal. So the perspective we're going to look at here is this. And once again, just for the sake of discussion, this is cysteine. And let me make sure I have the spelling right on this. Cysteine. Awesome. I was actually just talking to my wife this morning about exceptions to the rule of the I before E except after C rule. And there are many, many exceptions to that, and cysteine is also an exception. Yes, found another one. But yeah, the I before E except after C, unless you have a weird neighbor with beige pants on. Those words are exceptions to that. So anyway. All right, let's go ahead and do the Fischer of this. This is COOH on top. That is the most oxidized carbon. The question here I have for you guys is how many chiral centers are there? There's one. So you only put the hashes for chiral centers. A common thing I see people do, they'll put them for all the CH2 groups. That is unnecessary. Only do the crosses like this for the chiral centers, and you can just shorthand the rest. So I'm going to shorthand the rest of the molecule as CH2SH. Okay, which way is the amine group? To the left. Okay, so we can now give an R and S designation to this. We're actually going to give priority to the carboxylic acid group. Yep. Typically, oxygen groups get priority in most cases. So the question now is, what is top priority? Is it the carboxylic acid group, or is it the amine group? The amine group is. Yep. So first point of difference. So sometimes people get fixated on the oxygen here and they think that's the winner. It's by the first point of difference, nitrogen is higher priority. So priority 1. Priority 2 is the carboxylic acid group. And then there you go. So that RS.
Yes.
R? Yep, so it goes 1, 2, 3. It appears to be clockwise, but we're looking at the back because H is towards us. So this is an S designation. Would you say you can do the whole dextro-levo thing as well for amino acids? So what do you think, this is the L or D version of cysteine? It's actually the same kind of thing here. So instead of an OH, we're looking at the amine group instead. It's towards the left. It is L. An interesting little note here is that only the L enantiomers are biologically active in humans. The other one will, there's two things that our body will do with the other one. It'll either just push right through you, or it'll actually do some chemistry to flip the stereochemistry on that particular carbon. Our bodies can do that for certain amino acids, not all of them. So we can get it to work when we can, or not. But if you were to, say, eat a hamburger that had all the amino acids in there were the wrong designation, I think the only one that your body would take in is the one that doesn't have any chiral centers in it, which is glycine, is the only one that doesn't have any chiral centers in it. So all of the other amino acids, the carbon that has the amine acid on it, those are all chiral centers in amino acids. And once again, the L enantiomer is the one that is biologically active. So a little bit of biology for you guys to show you that stuff is related. All right, next here, the next problem I was thinking of is if you've been taking a look at the packet, it has some compound questions on there where I want you to do stereochemistry and then chair them both simultaneously. So here I want to go ahead and take a look at some examples. So let's go ahead and do that, and that, and let me go ahead and put an OH on here. Not idle, not idle. Okay. Okay, so when you're naming cyclohexanes or any kind of cyclo rings, I did show you guys about cis and trans if they're pointing in the opposite or same direction. The thing is, though, if you have more than two groups, saying cis and trans does not make sense anymore, because that's only referring to two groups. We have three here. So what do you think makes more sense to use instead? Actually, not E of these for alkenes specifically. it makes more sense to use R and S now. So we're going to have to use R and S here. The reason why is we have more than 2 groups. So anytime you have more than 2 groups, you now have to use R and S designations. So the kind of question I could ask here, and I think we'll actually leave class with this today, we're about out of time, is I want you guys to draw the most stable chair conformation of that compound and assign R and S for those. And you never know, a question like that might end up on the quiz.
Most stable what?
One like this is going to be on the quiz now, I think. All right, so let's go ahead and stop here.
What was the question?
One thing on this one, draw the most stable chair conformation and assign R and S to each chiral center. That would be good practice. And if you take a look at the packet we have online, there are a couple of them of this type that you guys could practice with if you wanted more. You're just dying for more practice problems. You need more practice. All right, guys, we are technically done with all of the content ready for the exam. So what is the exam going to cover again?
Just nomenclature.
Just nomenclature, right? Yeah, right. You wish. So we had nomenclature. What else did we have? We had acid-base chemistry. Do not forget about acid-base stuff. And what else did we have? We had all the 3D stuff as well. And this class has a tendency to be cumulative in nature. I did mention that early in this semester that we kind of keep building on each other. If you guys are having a hard time with this stuff, you really need to get this stuff under control, because after this test, we're going to take everything we talked about so far and wrap it in a nice bow and start talking about some reactions. Well, so after this stuff, we are now finally ready to start talking about reactions in organic chemistry. So even the stuff with the acid base, we're technically still not in reactions quite yet. So that stuff happens after this test. That's when students typically have a really hard time with this class, because everything now comes together. Things matter. So the thing is, the first reaction we're going to go over talks about how stereochemistry changes in reactions. So if you can't do stereochemistry, how could you possibly do reactions, right? So that's actually what we're starting with after the test. So just giving you an idea of what's coming ahead. So the class is cumulative. Everything is cumulative class. It just builds and builds and builds and builds and builds.
Should we expect IR spectra on the quiz?
Yes, there will be an IR spectra question on every single test until the end of the year.
No, I want the quiz.
How is that related to this?
On the exams.
Yeah, but how is that related to the
It's still organic chemistry.
Okay.
I'm going to put the spectroscopy question on every single test.
Okay.
Yep. Yeah, until the end of the year.
On the quiz then?
Not on the quiz. Quiz always focuses on what is current, and the exam does have built-in review stuff because it's relevant. And I will always have a spectroscopy question on there. So IR, and then the last test will have IR and something else, because we'll have the other spectroscopy by then. So, all right. So have a good weekend. I will try to get current on YouTube here within the next few days, and study, study, study.